Hello makers. This is the fourth video in the D-0 series that I've been producing. This is all about the coding of the Arduino and controlling our Adafruit controller, the various servos, the sound module, and receiving info from the FlySky remote. I've shown in the last video the electronics and how it was all assembled and installed, so this video will go through the software. What we've got in front of us at the moment is the program. I'll upload this to GitHub and I'll put a link to that in the description. First thing we needed to do was include all of the libraries that we'll be using. I'll also link to some of those because some of those are from GitHub as well. In one of the examples for the DF Mini MP3 player, they had a class that you had to implement within your own program, and it just reports errors from the SD card mostly, or the player itself. I actually put that into a separate header file to create that class, and all it does is literally prints out error messages to the standard serial, the hardware serial. We also need a software serial because we're using multiple serial ports and there's only one hardware serial on the Arduino Nano. We're going to use software serial, which this one I've defined as MP3 serial, and it uses pins 8 and 9 for that. Apparently there's a bit of a conflict if you try and use those two pins on a Mega, but seriously, why would you? There's 4 hardware serials that you can use on a Mega. We also need the FlySky iBus library created. That'll be using pin 10. And we've actually defined the minimum and maximum expected output on each of the channels. Now it's in microseconds. It's actually reporting microseconds. And when you look at an RC servo, they will have a pulse occur approximately every 20 milliseconds or 50 Hertz, but with a pulse width of between 1000 and 2000 microseconds, or 1 and 2 milliseconds. With servos, it does not matter how frequently the pulses come in, it is the duration of that pulse that counts. It is not duty cycle based. So if your pulses are coming in faster, say 100 Hertz, as long as the pulse width is correct between the 1 and 2 milliseconds, it will actually report the same, or move to the same position. For that reason, I've got a little bit more code further on to help us if we decide to run at a higher frequency. I've actually listed what all my channels are used for coming off the FlySky iBus and where they're connected. As you can see, I have one spare channel that I haven't assigned, and we'll look at using that in another video when I add in other library features such as pre-programmed moves along with sound effects. So I can turn on that switch, then use the mode select to select which routine I want it to play and then execute it. But that'll be for another video. Not every servo we want running the full width of its or full length of its travel. If you do that, you can do some damage. So for example, the head tilt, if you tilt it all the way, it will impact on the framework and you can damage your servo. So we limit that one. All the others I've got set for full range. The nod bar I probably do need to limit. I've managed to damage mine yet again, so I'll have to reprint it soon. Now let's look at the Adafruit PWM server module. Now this the chip they use in this was first and foremost designed as an LED driver, and it is a full proper PWM driver with the full range of 0 to 495, so 496 steps. By default it runs at 200 Hertz. We're dropping it back to 50 Hertz. Now, because I can alter the frequency to say 100 Hertz without too much trouble or impact on the servos, I've actually defined PWM min based off a calculation. Now, my first attempt at doing this resulted in some errors in the maths. While my maths was correct, the value exceeded the 32-bit number, and so the result stored in PWM min was not correct. So what I've had to do is divide the frequency by 10, which brings back to a realistic number when multiplying it by PWM, so it doesn't exceed that 32-bit boundary, and then we divide the result by 100 instead of the 1000. To get max, when I tried to rerun that calculation and multiply by 2, I ended up with negative numbers. Again, it's using an int and it's a 32-bit value. So in this case I took PWM min and just multiplied it by 2 to get PWM max, which is actually correct. We're looking at 1 millisecond and 2 millisecond. Now, one thing I did discover while reading through the data sheets and by trial and error is that there is a turn on and a turn off time for the outputs. And in this case, setting an offset of 12 from the calculated values actually corrects my offset, and it actually zeroes all of the servos, which is quite handy. I've made this adjustable because it's working off the internal oscillator, and I think that's part of the issue, and it may need to be adjusted for your own particular build. The DF Mini MP3 is again software serial in this case, and we had to link it to the software serial that we defined earlier up here. And then we actually create a few global variables. Now I'm using global so that I can access them in other sections as well, although I'm only using a few of them in other sections. Servo last is the last calculated position that we want the servo at, and it's actually the value we're feeding to the PCA 9685 chip. RC last is the value that was received from the remote control receiver. RC changed is an array that whenever we receive data in, we compare it against the last value we had, and if there is a difference, then we will update it and set that to true. On the next run through, we'll set it back to false. And then we've got the int MP3 track, and this is actually the track number that will be played. On that MP3 player module, it's expecting files to be named in a format of number.mp3 in a particular directory, which I've done, and this is actually the number of that track. Alright, so let's get into our setup. In our setup, I've got a lot of debugging in here because I did have some issues with the PWM. We're going to set up the hardware serial, a 115-200 board, and we'll print a message, D-0 robot control system. Then on the next line, we're going to print out what our calculated PWM minimum and maximum is, and the frequency we're planning on using. and it's also going to print out our raw PWM steps frequency. This is actually used as part of our calculations. We are planning on the PCA 9685 is an I2C device. In order to use it, we must be running the I2C bus, which is the wire function or wire library. So we need to start wire in order to use that library. The next thing we're going to start is the MP3 player. Now, one of the things I did find, again through trial and error and a lot of debugging, is that you need to start the MP3 player before you start the iBus. If you start them the other way around, the iBus crashes the first time it tries to do a read. After we start the MP3, we start the iBus, and then I start the PWM, in this case the Adafruit library. I could probably start the Adafruit library sooner, but I couldn't see any reason to push it any sooner. Pin mode 2 output. Now if you go back to the previous video, you'll see that I actually connected pin 2 to the enable pin on the servo driver. It's actually an enable low signal, that is, you need to drive it low in order to turn on the output. So in this case we're going to drive it high and disable the outputs from the servo driver until the system's up and running. Having completed all of that, we're going to have the MP3 module actually play track 1, which I previously set up here, and that is the path on the SD card and the file name. Okay, our main loop is pretty straightforward. We define RC changed as a Boolean value. That value will set to false at the beginning of the loop, and what we're doing is whenever any of the channels have changed, we will set it. We read the iBus serial, then we run a for loop, looping through every channel, and we will actually compare RC last with what's in the channel now. If they are not the same as dictated here, then we will copy the new value into RC last, set RC change to true, set RC underscore changed for that channel to true as well. Otherwise we will set that channel change to 0, or to false. Now we go through the fun stuff. If RC changed channel 0 or channel 1, that's our drive systems, have changed, we're going to do a little bit of mapping. We're going to map it left and right. Left, right and forward reverse. Now the maths that we want to do is going to be negative and positive numbers. The values coming off the receiver are RC min to RC max, or 1000 to 2000. The map function is really cool, and it will map it in a linear fashion to those values, minus 100 to positive 100. And we do that for both of those inputs. We'll use those in the next couple lines. So servo last 0 is, I think from memory, our left channel, and the other one's our right channel. One of our servos is actually going to be running in reverse, so keep that in mind with the program. And we're going to do a little bit of constraining as well. So we're going to map, I probably should have broken this down smaller to simplify it, but this single line does quite a lot of work. So let's go into each one. So forward reverse is our direction of travel forward or back, plus left right turn will alter the speed. either speeding up or slowing down based on whether it's the left or the right wheel. This is how we get our differential steering. For the other servo, we actually subtract left-right. So when you've got both of them going forward at the same speed and then you apply a left-right variation, one will speed up and one will slow down, causing it to do a turn. Now if this happens to be forward reverse happens to be 0, then we're going to add to one channel and subtract from the other channel the turn rate, which will cause them to actually turn one forward and one reverse, causing the robot to rotate on the spot. Of course, if it's already moving forward at full speed, what it'll do is slow down the wheel that it's reversing to the point where it stops. We don't actually reverse it. The next thing we do to that little bit of maths is we constrain it to be within the -100 to +100 range. We don't want to exceed that range. We don't want our motor to try and go to 200%, as an example. And we do that for both the left and right wheels. And then we map that -100 to +100 value, potential value, from that calculation after it's been constrained to the actual PWM min and max values. Now this is where they differ a little bit. Because one of the wheels is reversed, we've actually reversed the min and the max at this point, and this is where we get our reversal from. Now as I mentioned earlier, there is a little bit of an error within the PCA module, and that's what this PWM offset, or where we've applied it here. And so it stores all of that in last, and then we output those to the left and right wheels. Okay. There's a couple of ways we could have done our limits. I could have simply constrained, but as soon as you push, say, the joystick past that constraint point, everything beyond that is lost. It's not used. The other way of doing it is to remap it to our constraints, to our limits, and that way we get the full range of motion on the joystick mapped to a full range of motion on the servo within the range of that we're allowing. So what we've done is we've mapped, and we've actually done a double mapping. We've mapped the actual input, which has an input range of 1000 to 2000, to the nod bar range, minimum and maximum. And then we've mapped that result to the PWM min and max, plus the offset. And we've done a similar sort of thing for all of them, of those outputs. So that's the nod bar, the head rotate, the head tilt, and the main arm control. Channel 7 is our digital input. It's the left hand 2-position switch on the remote, and we use that for our servo enable. And all we're doing is when you drop the switch down, it turns the output pin down to low, enabling the outputs from the PCA module. Alright, RC9. This is the top end channel, and it's the button on the back. It's 2-position, either on or off, and whenever it changes, we drop into this section of the loop, and then we look to see if it was being pressed or being released. Now if it was being pressed, then we have a look at RC channel 6, and we actually decode that value through a function I wrote down later. I'll show you for mode select, and select the MP3 track that we're going to play. We're going to also make sure that we don't repeat this on the next loop through. So we're going to set that RC9 change back to false so it doesn't trigger again, and then we'll start that track playing that on the MP3 player. And finally we're going to print out our debug information, which is print RC values. Now this is our mode selected interpretation. So what we get from our mode set of switches, so we've got the 2 3-position switches, and each value that's output is configurable on the remote. And what I've done is I've configured that each value that will be put out through the combinations to return a value on the mode switch. And that equates basically to our MP3 channels and maybe to other functions down the track. And the last little routine we've got here is print RC values. This is a debug function. It's not absolutely required for the operation of D-0. All it's doing is printing out what we're getting back from the RC receiver and how we translated that to go to the servo. So when I bring up tools, serial monitor, I'll bring that down so to where you can see it. What you can see is the values that are coming off the receiver. So if I push the stick forward and back, you can see this channel here, channel 1 as it's known, is moving up and down, but it is altering this channel as well for the PCA, and that's for the output to the servos. I've currently got the output from the PCA module disabled, and that's this channel over here. So while it's disabled, it's not going to run around, so I can play with these controls. Now if I move this control left and right, this is the 0 channel, you can see how it alters both of these in a linear fashion. And remember, one motor's going backwards, so if I push forward on this stick, you'll see one goes down, one goes up, and that makes one motor go forward while the other motor goes reverse at the same rate. Pulling it back goes the other way. We've got our head rotate located here. Nod bar is located on our third channel in, channel 2, 3. This is our trying to remember if that was head tilt. And then we've got the main bar movement. So you can see everything's translating through. Now if I were to change the frequency, this whole system recalculates and the value you see in the brackets will be different. But we should have everything still nice and stable. We may have to retune the offset. And that's about it. So that covers this one. Mode switch operation is over here, and you can see it change. Now the MP3 player is not constrained by the enable, and so I can play sound effects by pressing the N button over here. And you'll see it's only when it goes to 2000 that it triggers the play. So that's the basic code that we've got in here. There are a couple of little things that I'm not happy with the operation of, such as when the robot starts to drive forward, it has a bad habit of tilting back first. This is a inertia and gravity, so as the body starts to move forward it's got to accelerate the head, but the head lags behind, so it tilts back. Unfortunately, the only way to get around that would be to put something like an inertial measurement unit in there and have that compensate for us by tilting the head forward as the robot starts to accelerate. And I think we might look at that for one of our next videos on the D-0 series. That'll do for this video, and I'll see you in the next video.